can see down here. Okay, so the material will not yield. Okay, so or it's at the boundary. Okay, this is at the limits already, right? So if we look at point number 2 now, okay, if you look at point number 2 is interesting. Okay, point number 2, right? So I'm going to write down here. So point number 2 is where stress A is equal to stress U, right? And stress B is going to stress U, right? This is a situation where you will not get a circle, okay? So I'm going to still draw the same limits, okay, same operating limits. Right, so this is our normal stress. Okay, normal stress, shearing stress element rotate clockwise, counterclockwise. Then I'm going to sketch our operating boundary. Right. So for this case, stress A and stress B are at the same point. Okay. So for this case, you will not get a circle. You just get a dot because stress A is equal to stress B. So this is our stress A and stress B. Again, it is at the boundary. The material will not yield. Okay. Now let's look at point number 3. Okay. So point number 3, you can see down here that the stress A and stress B are the same, right? Are equal, and they're half. Okay, half of the yield. So point number 3, where you have stress A is equal to stress B, and both are positive, stress U divided by 2. Okay, so both are the same point again. So for this case, I'm just thinking this might not be the best example, but it's okay. Clockwise, anti-clockwise, normal stress. Then we have the box again. Right. So again, we don't get a circle down here. We just get a dot, right? Because at this dot down here, stress A is equal to stress B, but it's operating within the limits. Okay, inside the red box, or it should be red. Inside the red box is okay, right? Outside the red box is where we have issue. Okay. Make sure it's red. Now I'll pick another point. As I said, that point is not so exciting. Okay, so I'll pick another point. Okay, so I'm going to call this point number 4. Okay, I'm going to pick another point. Right, now point number 4 is the same thing as point number 3, except one is positive, one is negative, and then we put point number 5. So let's look at point number 4 now. Okay, so I'm going to sketch point number 4. Maybe I'll come below. So point number 4 is where your stress A is equal to minus stress Y divided by 2, and your stress B is equal to stress Y over 2. Right, you can see down here. So point number 4, A, right, stress A is minus, stress B is positive. So what happens? Okay, so now you can see the circle shifting. Okay, you can see the circle shifting. So now we're going to look at okay, so this is our normal stress. That is our shearing stress. clockwise and anti-clockwise. Right, again I'm going to draw the red box. So our circle has to be within the red box. Okay, so now we know that over here, this point over here, this is our stress A, right? Over here, this is our stress B. And then when we draw a circle, right, it's shifting, yes or no, right? Okay. So this is also within the bound. That's why it is a slope. What I'm trying to explain down here. That's why this is a slope. Okay. It cannot be. It cannot be a not a slope. If it's not a slope, right? If you okay, let's do one. Okay, one that's outside. So now let's say now we have what over we have half. Okay. So let's say we do a point down here. Okay. So this is our point 5. Keep on changing my 0.5. I think that's more interesting. So if we have a 0.5 over there, what will happen? Okay, so if we have a 0.5, okay, so 0.5 stress A, right? 0.5 stress A is equal to minus stress U over 2. And then point B or stress B is equal to stress yield, right? Stress B is equal to stress yield. Okay, I'm correct. So now again we draw more circle. Okay, normal stress, shearing stress clockwise and anti-clockwise. Okay, and then this is our operating bracket. Now let me just briefly remind you, okay, that this operating bracket that we just draw in red, okay, so all these values are material properties. Okay, and the circle that we draw is from structure or stress analysis. So it's what you calculate. Okay, material properties is from where? Material properties is from handbook. Okay, now coming back to here, right? So now our stress A is over here, right? Now stress B is over here. So when we now draw the circle, as you all can see now, right, it's going to be outside the what? Outside the box. Right? So when this is the case, right, when this is the case, the material, so because the circle is outside the box, right, it's at this region, it's outside the box, at this region, it's outside the box. Okay, the material will yield, okay, or plastic deformation will occur. Okay, so I think this is a good visualization on why or how Tresca drew this box or drew this map, okay, the operating map. Okay, so now we know how Tresca operate, right? So we are going to we're going to look into one of the examples now, okay? We're going to work into one of the examples. Anyone, any questions so far? Anyone, please? No, I don't hear nothing. So we're going to look into example number 1. And this example is available on Avenue to Learn. Okay, and this is a 3D problem. Okay, repeat again. This is a 3D analysis problem. So I'm going to say this is a 3D analysis problem. Okay, so we are given a structure, okay, the internal loads and a critical section along a steel drive shaft. Okay, so when you see the word steel, okay, it's going to be a what? Ductile material. Okay, that's why they use the word steel. They highlight that this is steel. Our shape are calculated to have a torque. So we have a torque of 2,300 pound-feet of torque, and then we have a bending moment of 1,500 feet, and an axial thrust of 2,500. Okay. Now, given that the yield point for tension, okay, is at 150 KSI, and the shear is at 50 KSI, determine the required diameter of the shaft using the maximum shear stress criteria. Okay, so this is the problem that we are going to solve. Okay, so this is a typical question that you'll get, okay, or in a real life engineering world. Okay, so now we know that the maximum shear stress criteria is also known as what? Tresca. Right? It's also known as Tresca criteria. Right? So we have to, based on Tresca, let's see what was the assumption by Tresca. Okay, so the assumption made by Tresca is the normal stress in yield in tension is equal to the normal stress in yield in compression. Right? That was what I mentioned before. Right? That was the assumption he has made. Right? And then given that this is equal to 100 times 10 to the power 3 psi. Okay? And then the next one is the shear stress in yield is equal to 50 times 10 to the power 3 psi. Okay? Right. So for this case, can anyone tell me why we cannot? This is a shaft, right? Why, for this case, we cannot use the formula? Remember, we have the formula where radius of the shaft right, which is equal to C is equal to 2 over pi multiplied by a square root of moment in the y squared plus by moment in the z squared plus by torque in the x squared divided by normal stress allowable, or shear stress allowable, sorry, or maximum shear stress. Can anyone tell me why this cannot be used? Anyone? Based on the structure that we have, right? I taught you guys this before, yes or no? In shaft design, but we cannot use this formula at all. Can anyone tell me why, please? Anyone?
Because we have axial loads.
Yeah, Jindal, very good. we cannot use this because there is a what?